Hi, this is Mr. Roberts at Shasta High School, and I'm here to help you figure out how to add rational algebraic expressions. So we begin way back here. Part of the problems with understanding how we add rational algebraic expressions is really ensuring that we understand how we add, fractions. So I'm going to talk about a way that I like to detail that I think helps with adding fractions, and maybe you'll choose to use this way. We understand that if multiplication was simple, right? If we're multiplying two things, we're simply multiplying the numerator times the numerator, denominator times denominator. In the case of addition or subtraction, before we can combine things or take some things away from another thing, we need to have the same denominator, that which names the fractions. So here I've got 11 of these things called 12ths, 11 twelfths, pretty close to the number 1, and I've got 3 of these things called eighths. In fact, if I had one more eighth, that'd be a half. Before I can take away these from the 11 twelfths, they need to have the same name. And I have to be careful not to change the value of either one of my fractions, right? So I'm going to recommend, and this may be silly with the fractions here, but I'm going to recommend in all cases, go ahead and write numerators and denominators in factored form. So I'm going to write 12 as 2, 2, 3. 2 times 2 times 3. And my numerator factored is 11. Over here, I'm going to be, well, it doesn't equal anything. I'm going to be subtracting. Over here, I'm going to write, that's twice, one more time and I'm done. I'm going to be subtracting 3 over 2, 2, 2. Okay, now once I have it written in this form, I'm looking at each denominator and they need to be the same when I'm done. And all I can do is add factors to them in my attempt to get them to be identical. As I look at this, I can see that it has 2 factors of 2 and a single factor of 3. Over here I have 3 factors of 2 and no factors of 3. Well, in order for them to be identical, this number is going to need to pick up an additional factor of 2. So I'm going to multiply this by 2 over 2. And if you look at it now, here I have 1, 2, 3 factors of 2, like I have 1, 2, 3 factors of 2 over here. This fraction is going to need to pick up an additional factor of 3, or a factor of 3. It doesn't have any right now. So I'm going to multiply this fraction by 3 over 3. And now as I look at my denominators, I can see both of them have 3 factors of 2 and 1 factor of 3. This one has 3 factors of 2 and a single factor of 3. The beauty of this scheme is if you look at it, I've only multiplied my original fractions by the number 1. In this case, the number 1 in the form of 2 over 2. And over here, I've multiplied it by the number 1 in the form of 3 over 3. We know that because of the identity property multiplication, when I multiply by 1, I'm not changing this fraction at all. It's exactly as it was. It has the exact same value. And in fact, you might be like, hey, I could cancel this out. Yeah, don't do that. We're trying to add these factors so that they have the same denominator. But you're right. We could cancel out these factors of 3 and 2, and we'd be right back where we started to. And that's ideal because we want these to be the exact same problem. Now, as I look across my numerator, I can see that here I've got 2 times 11, and I'm going to go ahead and write that as 22. My denominator is still 2, 2, 2, 3. And 2, 2, 2 is 8 times 3 is 24. Over here, I have a numerator of 3 times 3, which is 9. And below, I have 2, 2, 2, 3, which is 8 times 3, or 24. This is exactly what I wanted. I'm so happy because now I have identical denominators. So I have 22 of these things called 24s, and I'm going to take away 9 of these things called 24s. And 22 take away 9 is 13. So I'm left with 13 of these things called 24s. So this answer is 13 24s. Okay, now to the algebra, right? Preliminary, just kind of looking at how we get common denominators and how we proceed. Let's look at this problem first. I don't think so. We'll come back to that. I want to look at this one because this has the problem that we just dealt with, right? I don't have common denominators. Well, in order to figure out what factors are needed in each of the denominators, I really need to see the denominators in their factored form. So this one's fortunately already factored. It's just x plus 4. This one, not so much. So I'm going to factor this. And this is a pretty straightforward problem to factor. If you find that you really struggle with factoring, particularly if you've got a leading coefficient that's not 1, why don't you look up some of my videos on factoring techniques. But right now I'm going to go ahead and look at the product of AC. The AC method here is -4. And this value right here is 3. So in this method that I teach in class, the trick is to find two numbers that have a product of -4 and a sum of 3. And as I look at these for a moment, the number 4, it has the factors 1, 2, and 2. So these are the factors I can play with, I can break up to get 3. And I'm pretty confident that one of them is going to be a 4 and one of them is going to be a -1. So I'll break it up like this, -1 and +4. And you can see when I multiply, I do indeed get -4, and when I add them, I get +3. What that tells me, because my leading coefficient is 1, I don't have to do factoring by grouping, which is the next thing I would have to do. But because A is my leading coefficient is 1, this is now good and factored. And of course, with any practice, you can see this just by inspection, that the factors are x minus 1 and x plus 4. Because when you sit here and you write this, you're like, that's x squared, that's 4 minus 1 is 3x, and then -4. Yeah, that's exactly what it should be. And my numerator is x minus 3. And over here I've got the 2x, and my denominator is x plus 4. Now that I have everything in their factored form, I can look at my denominators. I can say, aha, this denominator has a factor of x plus 4. This denominator has also a factor of x plus 4, but it's got an extra factor of x minus 1. So in order for me to get these so that I have the common denominator, this fraction is going to need an additional factor of x minus 1 in the denominator. So the trick here is just like we did with our numerical example. I'm going to place an extra factor of x minus 1 in the denominator, and to ensure that I don't change the value of this fraction, I'm going to match it with the exact same factor in my numerator, because as long as this expression is defined, it equals 1, in the exception that if x equals 1, I've got a problem. But in all other cases, x minus 1 over x minus 1 equals the number 1. So as I look at this now, I can see this is glorious. I'm so happy. I've got x minus 3 of those things plus 2x times this of those same things. So I'm adding these kinds of things. And it's like, what are these kind of things? Well, yeah, it's a complicated name. It's not like the numerical example we were looking at here, where we had, for example, 12ths and 8ths, and they became 24ths. Here we've got x squared plus 3x minus 4s and x plus 4s, and together they're going to be, those. That's my common denominator. So let's go ahead and write everything over a common denominator. So my common denominator is x. I didn't want to use red. His common denominator is x minus 1 times x plus 4, x minus 1 times x plus 4. And all of this is over, I've got a numerator of x minus 3 plus, now I'm going to go ahead and take 2x and multiply it by this binomial. So 2x times x minus 1, which is plus 2x squared, and then minus 2x. And the last thing I'm going to do is I'm going to look across at my numerator and see if I've got any common factors, and I do. I've got a negative 2x and a positive x here, so I'm going to combine those. And I'm also going to rewrite it in standard form. So I've got my descending powers of x. So I'm going to start with a 2x squared, and then I'm going to have a minus a single x, right? Because negative 2 plus 1 is a minus x, and then minus 3. And all of this is over x minus 1 times x plus 4. Now, it could be you look in the back of the textbook if you're trying to check your solution and you don't see this. One of the things to consider is perhaps they went ahead and multiplied these binomials. So an equally valid answer would be 2x squared minus x minus 3 over, you could say this would be x squared plus 3x minus 4. That would be fine as well. Okay, so pretty pivotal problem here. This is meat and potatoes what we're looking at. Let's look at another one here. Well, that's different. Let's go back up and look at this one. So we've got a much simpler case if our denominators are already the same. So you can see here I already have identical denominators, so I can go ahead and just bring this in and subtract. The one thing that's really tricky, you got to make sure you're paying attention to this when you're subtracting, is be careful, because I have here 3x minus 4, and I'm subtracting this quantity 6x plus 1. So I point this out because it's not just a negative 6x, it's a negative 6 times x and a minus 1. So this negative needs to be distributed to both of these, or it's minus 1 times each. So if I write this without parentheses, this would be 3x minus 4 minus 6 times x and then minus 1. And looking at this numerator, I can see that I can simplify it. I've got 3x minus 6x, which is a negative 3x, and then I've got a negative 4 and a minus 1, which would be a negative 5, and my denominator is still x squared plus 1. I think I have time for just one more quick problem here, by multiplying by the reciprocal of the denominator. And you could think about this as, if I have the number 10 and I'm dividing that by 1/2. I love saying this. What's 10 divided by 1/2? And it's like, oh, it's 5. Actually, think about it. 10 divided into halves is actually 20, right? Because there's 20 halves inside of 10. So when I have a number divided by a fraction, right, I can turn this into a multiplication problem like this. So you can see, yeah, 10 times 2 over 1 is 20. So 10 divided into halves, there's 20 halves in there. So I'm going to be doing that over here. I'm going to turn it into a multiplication problem. But I also have a little bit of a compounding here, in that my numerator has 2 separate fractions, and I need to get these together as a single fraction before I proceed. And when I look at it, my denominator here has a single factor of x, and this denominator has a single factor of 2 and another single factor of x. So I can see what I'm missing from this first fraction is a factor of 2. So I'm going to multiply this fraction by 2 over 2, i.e. 1. I'm not changing anything. And this numerator then will become 2 over 2x plus 1 over 2x. Very clever, you say. Well, maybe you don't say that. But you'll now notice I have common denominators here, and I can rewrite these as 3 divided by 2x. My denominator here is exactly as it was, right? I'm going to be dividing by x plus 4 over x minus 2. Okay, now comes the multiplication. So I'm going to rewrite my numerator, 3 over 2x, and I'm going to multiply by my denominator, which is x minus 2 over x plus 4. And now we have lovely multiplication of fractions. I'm going to multiply this numerator times this numerator, which would give me 3x minus 6 if I distribute. Again, the distributive, you can see here, I'm taking the 3 and I'm multiplying each one of these 3 times x and 3 times negative 2. And then the same thing here, I'm going to go ahead and multiply this 2x times x and this 2x times 4. When I do that, I get 2x squared plus 4x. I'm sorry, plus 8x, because 2x times 4 is 8x. So there you go. I've done this, gotten rid of this complex fraction. I don't have a fraction with fractions. I just have now a numerator and a denominator.